honors chem. Yes, honors chem. Okay. All right, so anyway, we're starting a new chapter. And you remember last chapter I said we're actually getting into another level of chemistry. This is now another level. So another level is, you might even call this the first real chemistry chapter. The rest of the stuff is important. It's stuff that leads into chemistry. But if you take a look at this, we're getting into chemical reactions. Now that's when chemistry occurs, isn't it? Yes, I want you to know how to write formulas, but where's the chemistry in writing a formula? That's just a skill, isn't it? And so what we're getting into this, and I do want to do some labs where you do have chemicals that react and they form products and things like that. So now we can get into for the rest of the year, we get into what you might call real chemistry, where things actually react with each other. All right, so here we go. I know it's last period of the day, but man, look at the sun, huh? Come on. You got to feel a little bit good. You get out of here today, go home and relax, be outside a little bit. It's probably around 50 degrees. All right. All right, here we go. Number 1, chemical symbols. In the first 2 weeks of chemistry, you had to learn these symbols, okay? But what do they represent? When I see AU, that's just 2 letters, isn't it? But they represent what? The chemical symbol represents, what do you think? What do you think? What do they represent? What do you think? Olivia, what is it? What does that represent? An element. Okay. Let's do the next one. What you just got done doing, chemical formulas. What if I write NaCl? That's just some letters on a paper. What does it represent, Todd? Right. And then now this chapter is this. Look at that right there. Whoa, look at that thing. What's the name of that thing? Not chemical symbol, not chemical formula, but chemical equation. All right, let me ask this. Isabella, what does that represent? What does a chemical equation represent?
Chemical reaction.
Right. See that? There's no real chemicals on this paper, but when I write it that way, it represents a real chemical reaction, doesn't it? So now we're going to do the first day of any chapter. You want to get some of the vocabulary words down, so we're going to do that. So we got that down. And I noticed that this little arrow, we'll talk about the arrow in a minute, but I see things that are on the left side of the arrow. See that? What do you call the things on the left side of the arrow, the chemicals that are going to react with each other? What would be a good name for them? What do you think, Victoria? Reactants. So if I said, look at the reactants on that equation, you say, oh, you mean over here? Yeah. What do you call the things that are going to be produced? What do you think, John? What do you think is going to be produced? Now we got the vocabulary down, aren't we? We got that down. And then we noticed that sometimes you might have to add some additional symbols to the equation. Now, for example, you're actually going to do this one. You're actually going to put zinc in hydrochloric acid, and you're going to form these 2 things. Here, get that? Okay, Will, can you put your head up, please? Now, what information am I giving you about the zinc? What form is it in? What's the S stand for? See down here? It means, and it'll be actually a solid piece of zinc, and you'll put it in there. What about this right here, AQ, and here's another AQ. What is AQ? And by the way, the person who typed this, it should be little a, little q. There's 2 typos that I found. Little a, little q. What does that stand for? And you said, well, I see the word aqueous. What does that mean? Dissolved in water. But what does that mean as far as you? Like, I'm going to give you some HCl AQ. What's that going to look like? And I want you to think about this, because think about this. What does this look like? And what does this look like? What does this look like? What do you think? Kieran, help me out here. What does that look like? NaClS. Have you ever seen that before? At your house, do you have a salt and pepper shaker? Okay, so have you ever seen table salt as a solid? Okay, so everybody knows what table salt looks like. It's solid, but what does this look like, Kieran? And I'll give you a clue. Have you ever put some salt in water and taken a spoon and going like that? What does it look like? What does it look like? It looks like water. This one does not look like water. This one looks like water. And so the extra information tells me what form something's in. When you guys do this reaction, look at here. You're going to take solid zinc and put it into a solution. It's going to be a liquid of HCl. It's called hydrochloric acid, isn't it? And then you're going to produce H2G. It's going to be gas. There are going to be millions of little tiny bubbles. In a minute's time, just hundreds of thousands of little bubbles are going to appear. And those bubbles are the gas called hydrogen gas. But what's this look like? What's the zinc chloride aqueous look like? What do you think? Anybody have an idea? Finley, what do you think?
I think it would just look similar to water.
Me too.
It'd just be like
Me too. If it's dissolved in water, it might change a color, but it's going to be clear. You'll still be able to see through it, or it has no color, like that. And that's why you add these little extra symbols to let you know what's going on here. Okay. Now we go down to the arrow. All right. How many people remember that? Maybe some teacher and it stuck with you, and you feel proud that you remember what the arrow meant. Anybody here remember what the arrow stood for? I know some of you did. Some teachers said it, and you said, I can remember that. What is it?
energy.
What?
Energy.
One more time.
Energy.
No, I don't think so. Have you ever heard a teacher call the arrow, it starts with a Y, I, E, L?
Yields.
Yields. Have you heard yields?
No.
Oh, okay. Well, anyway, when I was in school, even in college, they used the word yields because somebody taught them that too. But the problem with the word yields is, what does that mean? What does that mean?
A yield is a product.
And so it can mean that. It means it's going to make something, isn't it? So what does the arrow mean? It means yields or produces or makes or forms. See that? The arrow can mean many things. Another thing I want you to know about the arrow is there's a time aspect involved here. Anything on the left side of the arrow, they have not reacted yet. But what if I go to the right side of the arrow? The reaction is done. So this is before the reaction, this is after. And one more thing about the arrow. What if you have something that's not a reactant and it's not a product, but I need it to be there? And if it's not there, the reaction won't take place. Like, what if I said heat? Heat is not a reactant. It's not a product, but if I don't heat this reaction, it won't happen. What if I said, I don't draw it very well, but what if I said you needed electricity? That's not a reactant. It's not a product. And so I put it on top of the arrow. You see that? Here's what you did in ninth grade. Ninth grade. Carbon dioxide plus water yields glucose plus oxygen gas. But you aren't done yet because I'm sure Miss Fallon said something like this. You also need what? Chlorophyll. Remember that? Remember the green stuff in leaves, chlorophyll? Is that a reactant or a product? Neither. Matter of fact, it's going to absorb energy and release energy. Absorb energy, release energy. It's not a reactant and it's not a product. And then she's probably talking about light. Is that a reactant or a product? Neither one. And then she might have even said this. Almost all biological reactions need enzymes. Did you ever talk about enzymes? Remember catalyst? Ever heard that word, catalyst? Enzymes help a reaction to take place. They're not a reactant. They're not a product. As a matter of fact, when they get done, they're ready to do it again. You're going to do an experiment here where you're going to let something decompose. And what you're going to do is, if you let it sit by itself, it'll decompose very, very slowly, very slowly. But if you put a catalyst in there, it'll react and decompose very quickly. And now what happens to the catalyst? It's still sitting there in the beaker. And if you want to use it again, take it out, put it in, it'll do it again. So a catalyst is not a reactant, it's not a product, but it is something that helps a reaction take place. Okay, next thing I want to do is, we said it was called a chemical equation. And my question to you is, what's equal? What's equal? You said it's a chemical equation. What do you mean? What's equal to what? Have any ideas about that? Look up here. What's equal to what? What do you see? What do you think? Yes, yeah.
Alright, so both the reactants, they're equal to the products.
Say it again.
Both of the reactants are equal to the products.
How are they equal? They don't look the same. Like this one has zinc, and this has zinc chloride. This has hydrochloric acid, and this says, they don't look equal to me. Now, I'm asking questions you probably didn't have this asked before. Middle school, there's no way they're going to ask this. Yes?
I was gonna say that like during kind of a chemical reaction, like when you
Say it one more time.
like you can't find new elements and stuff in chemical reactions, you can only make new things out of old things.
Do you think that the chemicals over here, are they the same as the chemicals over here? And if you do, they'd have the same names. Do you think the chemicals themselves are equal or the same? Like this is called zinc, and this is not zinc. That's zinc chloride. The chemicals themselves are not equal. So what do you think is equal? If it's not the chemicals themselves, a guy in John Dalton, 1700s, one of his statements said, and I don't know how he came up with this, he said, in a chemical reaction, what happens to matter? What happens to atoms? Do atoms ever get destroyed? No. Did atoms come out of nowhere and be created out of nothingness? No. What did he say happens to them?
Atoms neither created nor destroyed, they're always rearranged.
They're just rearranged. You see that? And what has to be equal then?
The amount of atoms. The amount of each atom.
Yes. So if you had a certain number of atoms that you started with, you have to have the same number of atoms that you end up with. You get that? So I want to show you something here. I'm going to try to draw this for you, okay? I'm going to try to draw this. I'll tell you what, let me draw it like this. Forget you see this right here. Forget that there's a big 2 there, okay? I'll talk about what that big 2 is this minute. I used to always, for many, many, many years, I would say, let's say you had a Tinker Toy set, and then all of a sudden, about, I don't know, 8 years ago, there were too many students that went like that, and would you be honest, tell me if you clearly, you absolutely know what a Tinker Toy set is. Raise your hand. Okay, that's why I have to be careful now, because a Tinker's I thought everybody knew what a Tinker Toy set was, but that's okay. Legos. What if I say Legos? 100% of you, right? Okay, so let's try it. I have one of those Lego pieces, and I have one of those and one of those, and I'm telling you, without that 2 being there, the way it's written up here, can you take one of those, one of those, one of those, rearrange them, and make that? Can you do that? Really? I can take one of those, and oh yeah, there's one over there. I get it. I can take one of those heart-shaped things, and all of a sudden I have 2 of them? How am I getting 2 of them? Where'd that come from? And you can take one of those stars and make 2 of the stars? I can't do that. So even though we write the chemical equation, we're not done yet. It didn't tell the whole story. We have to do one more thing to a chemical equation to make it true. And what we're going to do is we're going to add these numbers in front. Now sometimes we don't add a number and we know it's 1. If it's not 1, I'll let you know. But look at this right here. What if I said take one of those Legos and 2 of these? 2 of these. Not one of the HCLs, but 2 of them. Could I rearrange those and make this? Whoa, what? Yeah, that works. And so what we do is we added some numbers. Now, in math, what do you call the big set of numbers that you put in front of x's and y's? What do you call those in math? No, the variables are x and y. What's the big numbers in front of the variables? Coefficients. What do we call them in chemistry? Coefficients. I like that. So what you're going to do is you're going to learn how to balance an equation. If you look at this equation here, that does not make sense. You couldn't start with one of those h's and end with 2. But if I put a 2 here and I balance it, balancing, again, I never knew what balancing meant. I did a lot of sports and stuff, and the only thing I was good in PE class and all that, and I thought the only thing I knew about balancing was, we even had a gymnastic unit. You ever do that? I don't know if they do that anymore, do they? Okay, so we had to do things like balance beam and stuff like that. But anyway, that's the only thing I ever knew about balance. But if I'd asked my parents, they would have told me, oh, there's another way to use that word balance. I put $1,000 in our checking account, and the bank sent me a statement, and during that month, we wrote some checks. At the end, the bank sent me a statement that said, I wrote checks for $800 worth of stuff, and the little piece of paper said, I had $200 left in my account. What if they said I have no money in my account? I'm going to call them on the phone and say, you're out of balance. Balancing, the other way balance means keep track of everything. Everything can be accounted for, you get it? And so when you balance your checkbook, I'll say, I had $1,000 in there, and you better tell me where all $1,000 went. If I only spent $800, you better tell me I have $200 left. And that's what you do in chemistry, right? Look at this right here. If I started with 2 H's, there they are. I started with 2 Cl's, there they are. See that? On the thing on the left, the number and type of element on the left has to balance the thing on the right, doesn't it? And we'll be doing that too. It's called balancing an equation. That's kind of fun. And the last thing we're going to do is my first day of the new chapter. Okay, ready? Who says that that's going to happen? What is it in the real world that makes a reaction take place? What are the driving forces? What is it that makes it happen? And I'm going to try to teach you some of those. And when you get into the lab and you actually do some of these reactions, you'll say, wow, I know what happened there. And I'll say, here's one. Sometimes if you have a reaction and one of the products is going to be water. Water is a very, very stable molecule, okay? And that'll actually make that reaction take place, the formation of water. Okay, another one is the formation, and I'm not going to get into thermodynamics, but of a gas. And what happens is you have these things, they're going to react, they form a gas, and that can drive a reaction to take place. As a matter of fact, look at this right here. What do you think the driving force of this one was? See? Formation of a gas. Here's another one. Formation of a solid. And now what I'm talking about here is this. We're going to start with something as AQ. We're going to start with something that looks like water. It's going to be a liquid. And you're going to react it with something that is AQ. It's going to be another liquid. And they both might look like water. And when you get done, you'll have some material that is a solid. So the formation of a solid means you didn't start with a solid, but one of the products is a solid. And you'll like those reactions because it looks like you're pouring water into water, and all of a sudden some big chunk of yellow will happen. Where'd that solid come from? And that was the driving force there. And I'll come back to that one. I'm not ready to do that today. Yes?
What do the subscripts say?
The what now? AQ? So AQ up here, the extra S means I'm a solid, L means I'm a liquid, G means I'm a gas, AQ means I'm dissolved in water. It's called an aqueous solution. So these things here, you don't know this, but sodium nitrate, if I put it in water, you won't see it anymore. It's a solid crystal, and if you stir it in there, it'll look like it's gone. It'll look like water, but it's not water. And I'll do another one. Silver, let's see, wait a minute. Oh, well, I'm trying to make one up that'll actually work. That's not a good one. How about NaCl? Sorry. If I were to react NaCl plus silver nitrate, they both would look like water. They both would look like water. But what would happen is the silver would combine with chlorine, and it'd be like a white solid sitting in your test tube. And you know, I never saw a solid here. I never saw a solid here, but I saw one, and that was called a driving force. Well, anyway, that's the intro. That's called an intro to the chapter. Now we're going to go over here and let's learn some. There is one typo on this page. I'll show you when I get there. Okay. All right. Yes.
What was the fourth driving force?
I'm going to come back to that later. I thought for right now that's enough. I don't want to get into the fourth one right now, but I will. I will come back to it. All right. On the next page. One thing that humans like to do is they like to put things in groups, didn't they? Even when I was teaching you last chapter, didn't I have type 1 and type 2? And it made it easier to learn it. And so people thought one thing that would make chemistry easier is if I classify the different reactions. And what I do with first-year chemistry students is there are more than 5 types of reactions, but I just want to say 5 for you guys. We'll stop at 5. That'll be enough. There are a lot of them. A lot of the chemical reactions fall into one of these 5 categories. Now, this is actually easier than you think. You'll be surprised how well you'll actually know this after you only heard it one day. Here's the first one's called synthesis reaction. Okay? Now, synthesis means to take something simple and combine it into something more complicated. Okay, everybody in here should know that word, synthesis. And so it looks like A plus B yields AB. Now, let's go down to the real world and see if there are any of these down here that look like A plus B yields AB. Can you spot any of these equations that look like they might be synthesis?
Number 7.
Which one?
I said 3.
Oh, sorry, one more time.
I said 3.
3? Okay, take a look. A plus B yields AB. Very good. That was easier than you thought, wasn't it? Any others? Yes?
I have a question. Why is it 2? Iron 2.
Say it again.
Why is it iron 2?
This one? Now, even though we're classifying, what are we eventually going to have to do this equation? Yeah, eventually we're going to have to balance it, aren't we? I love that. I love what you just said because that's not good. You can't get 3. See, I love what you said because eventually we will balance the equation, but right now we're just classifying it. Excellent. Thanks for doing that. Yes?
6 and 7.
Oh, okay. A plus B yields AB. Oh, yeah. Oh, yeah. And what do you think, 7?
I think 7, but it could be something.
We're going to skip 7 for a minute because that's a little more complicated. I'm going to skip that one for just a minute, okay? All right, now, any others that you might think are synthesis? All right, let's flip it over. Look on the next page. Any of these that look like synthesis? Yes, Eloise. Yes, that was fast. Man, that was very fast. Anybody else see another synthesis? Yes.
2.
Which one?
2.
One more time.
2.
I'll tell you why it's not synthesis, because synthesis you have to have something plus something. And notice number 2 only has one reactant. How about another one? Another synthesis. Oh, okay. Claire, Nettles. 6. Let's take a look. This, A plus B yields AB. I like that one. Any others? Yes?
I was gonna say
4?
4.
Okay. A plus B. All right. Hey, that wasn't so bad. Do you think you might be able to recognize a synthesis reaction? Okay, let's flip it back over. What is the opposite of putting things together? And by the way, can I tell you something? Whether or not you thought this way last year, because remember you're only a 9th grader, and now you can think much better now. You don't think so? No, I'm the same. In every aspect, I'm the same. Now, I bet you write better. I bet you're a little better in math. I bet you're a little bit better. I bet you are. Wait till you're a senior and you see the freshman run down the hallway. You said, I used to be like that? Yeah, yes, you did. Okay? You'll see it as you get a little older. You just don't think you change very much, do you? Now, here's one. Last year in biology, they took something simple, carbon dioxide, and something simple, water, and they put them together, and if you had chlorophyll light and enzymes, it made something more complicated. It made glucose, didn't it? That was a synthesis reaction. And it needed light to happen. So they called it photosynthesis. Well, now that I know what synthesis means, that's a great name. That's a great name for that. You probably never I gotta go on. Stop. All right, what's the opposite of putting things together to make something more complex? What's the opposite? What now? What's the next one? Decomposition. To decompose, right? All right. You probably heard of Beethoven. He was a great composer. What's he doing right now? He's decomposing. Anyway, no, he actually already probably did decompose. But anyway, decomposition looks like this. Here's what I like about that. There's only one reactant. There's only one reactant. All right, find the decomposition on this page. I don't either, but I just wonder how long it would take people. So let's flip to the next page. Anybody have a decomposition over here? 2. Look, only one reactant. Decomposition. Any others? 9. Yep. Very good. All right, and even though this didn't break up into 2 things, it only had one reactant, didn't it? So what do you think? It broke up into many things, didn't it? Man, it really decomposed. All right, what do you think about decomposition? All right, let's do one more. How about that? One more. Sorry, I got started a little bit late there. The next one is called single replacement. Some chemistry books say single displacement. I like single replacement, so I'll probably say that. Single replacement. I think we're finished.